so the next part of our advection dispersion equation is advection. This is the transport of solutes in flowing groundwater. So this is the transport of solutes. Remember we talked about what a solute is by flowing groundwater. Okay. So this is what we also refer to is flow will be like in a tube or plug flow. It could happen. So if there's no reaction, there's no absorption, there's no biodegradation, there's no diffusion, there's no dispersion, nothing. It'll go by what's called plug flow. So kind of like moving through a pipe. It will go through in a straight, like a slug of it. So if it doesn't react, it just goes straight by Darcy's law. It just moves completely by that. It'll be what's called plug flow, and it'll just move in a unit. So say you have a spill of, let's say, you pick any, we'll make up compound X, okay, because we're just going to have compound X. So you have a spill of compound X. Here's your surface of your ground and stuff like that. The compound will move in the groundwater, but it'll move as a slug of it, because it's spilled into the ground here, and then it just moves as a group. It never disperses into the ground. It never moves anyway. It just moves with the groundwater flow completely. It moves as a slug. Advection mass flow, so basically it's using the governing equations from Darcy's. So what will happen is this will move with the average groundwater velocity. So this moves with the average, spelled average, velocity of the contaminant is going to be moving if it doesn't react from Darcy's law. So the velocity will equal divided by the porosity, the hydraulic conductivity divided by the porosity over dH/dL, where, Q is the specific discharge in units of length over time. K is the hydraulic conductivity in length over time. NE is the effective porosity. And there's no units on that. So there's no units on porosity. Generally, we always estimate, if we don't know what it is, to be 30% or 0.3. So most groundwater velocities will range between 0.2, or porosities will range between 0.2 and 0.35. That's the usual range, so that's why we always just say 0.3 is a good, like if you don't know what it is. And then dH/dL is your gradient. You're along the flow path, so this is your hydraulic gradient. And again, it has no units. Okay. So this will just tell you the average velocity that it'll move. So if you know what the specific discharge is, or if you know the gradient, so if you know the change in the height over the change in length, you know what the hydraulic conductivity is, and you can estimate the thing. You can estimate the velocity of this moving through the thing. And if you know how far apart, say, two wells were, so if you say you had one well here and another well here, and you spilled into here, say, sodium chloride, and you say, okay, these are 3 feet apart from each other, and you know the hydraulic conductivity, and you know your head difference between this one and this one, so you know your head difference, so you can figure out your gradient. You should be able to say how long will it take, because you'll know what the velocity is, because you remember hydraulic conductivity, even though it's the same unit as specific discharge and velocity is in feet per, it's a length, it's a unit length per time. You could be able to figure out how fast these things will move by advection. So there's no dispersion, there's no dissolution, there's no absorption, there's nothing. So just by effective flow. So effective porosity. We'll just go into that for a second. So effective porosity. I already kind of mentioned it, but effective porosity, or NE, is often defined as the porosity through which either flow or transport occurs. Okay, so this is the part of, so the thing with effective, notice I said the word effective, and this is where the either flow or transport occurs. So this is where the flow or transport occurs. So because of this, in granular soils, so in most soils, the effective porosity equals the total porosity. Basically equals the total porosity. Okay? But the thing is that's not always the case. So in a very nice sand, perfect sand and everything like that, then you might have the effective porosity be equal to total porosity. But once you have like soil aggregates, so once you have aggregates in there of soil, there'll be those, remember we showed this last time and we had the things going into here and we had the aggregates and made up of all the different things and we could get diffusion across these borders and stuff. Well, what is the effective porosity here? Well, it's really just that flow through the macropores. So, when you just have flow through macropores, then that tells us what the velocity is. If you say you had a fractured clay, what about if you had a fractured rock or a clay, where, what is the effective porosity? Okay, well, in some of these things, because the flow is only through the fractures, so, say you have all these fractures that are going through a rock here, well, the effective porosity here, the fracture porosity in this system here, say, is less than 1%, while the total porosity, because you took the rock and you measured the porosity of the rock, could be up to 50% for the total porosity. And so a lot of times, most of the time, especially like in fractured rocks, the effective porosity is very low compared to the total porosity. So this is why we don't use total porosity, but we use what's effective porosity. We should be cautious of the word because it's effective. So it's very difficult to do, to estimate this. This is why I just said, usually, if we're in a sediment soil and stuff like that, we estimate this at 0.3. It's just a fudge factor. So sometimes what you can do is if you want to figure out the porosity, there are different methods for figuring out porosity. From the soil scientist's point of view, they can take this and then they'll figure out the porosity of a soil. They can take a core and then they could do some testing with it. You could do where you control all other parts of the equation that I just showed, of this, and then you could figure out effective porosity for your system if you know all the other parts to it. You could estimate for your particular soil sample. You could model the system and then vary the effective porosity until your data matches the data you got, and then you can say, oh, okay, I changed my effective porosity, and okay, now my data looks like the model, and so that would be how you can use modeling in order to figure out some of these environmental conditions. It's very hard and stuff like that. So that is effective porosity. Now, draw a line here. The thing is that we really don't get effective flow in the environment. That really doesn't happen. We don't get this plug flow occurring in there because of when we talked about dispersion. So when we have advection with dispersion, which we already talked about, we're going to get mixing. And so what's going to happen is you're going to see the plume not go in as a plug. So it's not just going to march along like it did here, where, we could do this with time and say, at time, this time it was here, then it was here, then it's here, and it just moves as a plug. And so this is T equals 1, T equals 2, T equals 3. This is not what happens in the environment because we have dispersion. And once we have dispersion, what's going to happen is you're going to have your spill here, and you're going to have your flow going this direction, you're going to have a higher concentration in the middle, and then you're going to have rings around it of lower concentration. And you're going to have the highest concentration here in the center, higher concentration in the center. And you're going to see the spreading along there. So it's usually transverse to flow. So this dispersion here is going to be transverse to the flow in there. And so this is spreading of the compound. So we're going to have spreading. Spreading of a solute. So we're going to have, again, we're going to have spreading of a solute or a slug, both along the flow path. So also along the flow path, and transverse, and it's referred to as dispersion. So these things, the spreading of here, so we have our spill, our little gasoline. The spreading of it is referred to along the slug flow, the spreading that happens along the flow path and along the traverse part of it. It is caused by diffusion and variations in velocity of the flow. So we're seeing variations in flow. We already talked about that there's going to be a little faster and slower parts to it and everything like that. And so there's variations in velocity of the flow when we calculate Darcy's law. So when we use Darcy's law, we can calculate the flow just straight out. But once we add in dispersion, we're going to have to also take into account that there's going to be parts that move faster and slower. So when we look at this, one of the ways that we're going to be doing, I'm spending a lot of time, is we're going to be going through what are called breakthrough curves, or BTC. Okay, so we're going to be doing breakthrough curves a lot in this class. Okay, so when we look at them, usually on this axis, we have what we call C over C naught. Okay, so this is the concentration of the compound divided by its original concentration. So C over C naught. When we have 0, and say we have up here 1, and we have here 0.5. Okay. So when we reach 1, that means that the concentration in a down gradient well, so say we have 2 wells here. Okay. And we're going along a flow path. Okay, so this axis over here, say this is our distance along the flow path. So say we have a series of wells along the flow path, okay? And there's a spill that occurs over here. So spill occurs right at this first well right here, or right here in this first well where we're doing a measuring right here. This is what it'll look like. Then as we move down, it'll change as we move further and further away from where the spill occurred. When the concentration gets up close to 1, that means it's the concentration you put in. So let's assume for a second that we spilled something very quickly. We dumped a jug of, gasoline, we're changing the oil in our car, and then we had this leftover oil. We just poured it down a well, okay? Well, okay, or we'll use salt in this case. It's road salt time, it's winter, and we spilled some road salt down a well, okay? So this well that's the closest to that, we can say that the flow would come almost all the way up, and it would diffuse a little bit out. It assumes the concentration profile at T0, so this is T1. So what we're going to see is that the concentration is going to be a little bit of, it's going to be diffusion in here, it's going to come up to the top and then go back down. As we move further along, it's going to spread out more, and then at the last time, you don't have enough paper, but it'll even spread out even more, okay? We have to assume that the area of the curves remains the same, so the area under curves are the same. Okay, and so what this is saying at this time or this distance away from the thing is that, so the area, so my drawings are not perfect, so that's why I'm writing down these assumptions on stuff, is that the area under this curve is the same as the area under this curve, okay? And what we would say is that the mass isn't lost. It's not absorbed, it's not degrading, nothing's happening to it. It's just moving by advection and dispersion and stuff like that. What's going to happen is it's not going to reach that 1 anymore. As we get further and further away from it, it's going to spread out further and further. So it's a pulse injection. We're going to get lots and lots and lots of spreading. So we're going to have some of the molecules are going to move really, really fast. And they're going to actually be faster than the main part of the mass. So the main part of the mass is the highest point here, and that's going to be the center part of the mass. Now, if this was under advective flow, your breakthrough curve would look like this. It wouldn't change because it's moving, it's marching its way down the thing. So advective flow, you would have 1 over here and 0, and you would have all these different things that would just move from one well to another, and that's not what happens. What actually happens is you get this dispersion occurring, and so you get some of the molecules actually moving faster than the average velocity of the ground. So if we took our Darcy's law here, which gives us our average velocity, with dispersion into there, you're going to actually get some of the molecules coming through faster than the average velocity through there, and some will be slower. So on average, this becomes the average velocity, as I said in here. So when we calculate Darcy's law, usually we use the 0.5 mark as to say, okay, that is the average velocity. That's Darcyan flow is when this will come through. The center of mass will come through at this point here, at the highest point. So this is the average velocity. I'm sorry, not the 0.5. That's something else. We'll get to 0.5 in a few minutes here. And we get to the other ones. But the center of mass here is the highest point here, and that's your average Darcyan flow. Okay? So you're going to have with dispersion things coming in here. Note that the center of mass of the slug moves along with the average groundwater velocity. So this part right here moves with average groundwater velocity. So that's where that's coming through. This is the average groundwater velocity. The peak concentration is going to be highest at the beginning, and then it's going to get lower and lower as you get further away. And the solute protons in 2 and 3 are approximately normal distributions. So you should recognize these things as like normal distribution. Okay? So groundwater flow does not occur this way like it does through a pipe. So we see this diffusion and dispersion happening along the way. Okay? So examples of dispersion, say that you had one here. I'm going to hold on a second. Okay, I think I messed up. So I'm just going to walk through it again. So I'll have to check my video recording. I had drawn this out. Okay. Well, I'm just going to walk through it again. So it's good for you guys to hear it again if I recorded this twice. I don't think I did. Okay. So we have a source here of a pollutant. And what it is there's a constant source of it coming off of our contaminant. And what happens is we have a monitoring well down gradient from our source. When we look at the concentration over the not concentration of 1, it's usually very close. There's not a lot of diffusion occurring. It stays really close into there. And as we have what's called longitudinal dispersion, that contaminant is going to then be here at C over C naught of 0.5, C over C naught of 0.1, 0.1. So we'll get this longitudinal dispersion occurring as we're going through it. You can also get transverse, so this is transverse diffusion, that's what that word says there. Transverse dispersion occurring where it spreads a little bit out. So like if you were looking at this, we're looking at this in cross-sectional view, you'll get a little bit of it going up and down in there, but not a lot. Most of it is going to go with the flow of the water. So we have these stream tubes showing where the groundwater is actually flowing through that. And we're going to see it moving with the groundwater flow and getting a lot of longitudinal dispersion, but not a lot of transverse. It doesn't go up and down very thick. So really a plume will stay kind of at the same height. It'll go up and down just a little bit, but it'll go further out into the flowing of the groundwater. So we see a lot of longitudinal dispersion. That's what this is showing here and there. So if we go back to our breakthrough curves right here, so we have our breakthrough curves, C over C naught, so ours are 0 or 1 and our 0.5, and we look at the distance from the source. So if we're closer to the source, we'll have concentration really close to 1. As we're further away from it, there is no contamination in here. If we moved by advection only, it would be the green. And so what would happen is it would just all of a sudden at some point down gradient, distance from the source, there would be 100% of it, and then there would be none of it. So here it would be 100%, here it would be 0. But that's not what really happens. Because we have this longitudinal dispersion, what will happen is as we go further from the source, it'll start to disperse out, and we will get some into here. At the 0.5 mark is where this is the red line here. Change the red. The red here is advection plus dispersion, I'm sorry, and dispersion. And this one is advective flow only, is the green. Okay. So what we notice here is, and this is advection only, is our Darcian flow. It would come through at the 0.5 would be the same. Now, say if we looked at a lapse time at a well. So we're back here at monitoring well 1, and we're monitoring water coming out. We're going to have a little bit of it coming, and then this is going to move further into it, and then this, and then this. And so what we're going to see is we're going to see first arrival. This is our red here. This is the spreading due to dispersion. This is our flow. All of a sudden we'll see it coming up, and then eventually, if there is no retardation, it will reach that C over C naught of 1 in there. And so it'll go in and it'll come out at the same concentration. But due to dispersion, we're going to get some of it coming through beforehand, some of it coming later. But at that 0.5 mark is when we have it based on this right here, is based on advection. So this is the arrival time based upon advection. And then the rest of this is advection and dispersion together. So we have arrival time at the 0.5 is when it's calculated for the arrival time if we use plug flow. At a monitoring well, down gradient from it. And so these breakthrough curves tell us, so if we monitor a well and we're looking at a contaminant, we can make predictions as to how fast it's moving, or we can make arrival time look into it. We can understand the system by understanding our advective flow. So one thing I keep talking about is relative concentration. Let's see if I can do this. Relative concentration. So what is relative concentration? That's what I'm showing over here. It's that C over C naught. One of the things that we try to use relative concentrations a lot in contaminant hydro because it's comparing it to where we start from. It's a way of normalizing our data. So when our data is really kind of messy, we will do this compared to our beginning number in order to kind of smooth out the data, to have something relative to a number. Because we can compare, as you saw here, the 0.5, where that 5 is. We're going to talk about when it reaches this upper part here, first arrivals, and how we can use how something moves relative to each other by putting everything into relative concentration from the source. So relative concentration, let's see here. Relative concentration equals C at xit, so at a particular time and distance from it, divided by CB over CS minus CB. And we also look at this as C over C naught. Okay? So C xi comma T equals the solute concentration at some point in the flow system at time t. Okay? Cb is the background concentration. In the flow before we release the contaminant, so we either have to use a upgradient well, or if we're following a pollutant moving, we'll take it before the pollutant arrives there. A lot of times we use upgradient wells so we can get a background, because then we have to subtract out the background. So say if we're using salt, there's always a little bit of like conductivity or salt inside of the water, so we need to know what the background of it is. The CS is the concentration of a given solute at a source. So the concentration of a given solute in the source, usually constant unless specified otherwise. So this is just a constant in there. So if Cb equals 0, then the relative concentration is the concentration. Then it's the relative concentration is just the concentration. So C xit over Cs equals C over C dot. Okay, so if there is nothing in the background, then there's nothing for us to subtract out. Then it's just if Cb is equal 0, there's nothing in the background. But if there is background concentration, then we have to use this to subtract out that background so that we're getting pure relative concentration. Otherwise, this is starting up a little bit higher than where we started from. So this is more important like if we're using solutes, or we're looking at something that's already inside of the ground in there. A lot of times there's not background concentrations of gasoline in the environment, and if there is, then we got a bigger problem than dealing with this. So usually we're just thinking of the concentration over the concentration of the solute. We usually are not concerned about the background. But if we're dealing with like salts, because salts can be found in the environment, then that would be in there.